So this is 126. And yes, all right, here we go. And we're up to recognizing C constructs in assembly right here. So I should have that open someplace. All right. Be careful putting your key device in a bank safety deposit box. Sometimes the banks lose them. Yes. Yes. There was even an article I read recently where the police just went and raided all the safe deposit box in a bank and kept all the valuable stuff, seizing it under asset forfeiture, that if you had that stuff in a safe deposit box, it must be illegal. And so, yeah, it's a problem. You know, now that's one reason why you might want to leave it at Coinbase. It's somebody else's problem to physically secure it. I mean, if you put your coin in a cold wallet, now you somehow have to secure that physical object. It's like a bar of gold. Yeah, that's why, you know, there's no perfect safety in the world. Anyway, so, let me see if I got my machine running. I think I do. All right. Yes, I do. I can use it for demonstrations later. Anyway, so here's a simple function call. So if I just make a print hello here, and I also print a number and a string, so I print it with a format here, %t and %s, then this will call the printf routine with a couple of parameters, is the point of this. And so you compile this thing. All right. And now you can look at it in IDA Pro. When you first load it in IDA, you will only see the entry point. And I think I can zoom this in. Yeah. Let's make it a little. Yeah. So when you first zoom in with IDA, you'll just see the entry point here, not the real code. So then you have to do something like search for strings like we've done before and find the string hello. And then go to that area. And then you'll see the code that actually does the job, which is here. So what you do is you push, this is preparing the prologue. And so now it pushes an offset to hello onto the stack, and then it pushes 2. And the next one should show, here's the whole story. This is what the assembly code looks like for a function call. You push a parameter on the stack, you push another parameter on the stack, and another. You put them in reverse order. So the first parameter was the format string, showing you're going to print a decimal and then a string. The next parameter was a number, which goes in a decimal. The third parameter was the pointer to a string, which will then print as a string. So you push the parameters on the stack in reverse order, and then you call the subroutine, and this will eventually call the print. And you say, what is the a hello? That is the name that IDA Pro made up to assign to this variable. That's right. That's what IDA did. IDA makes up a name for it, and often they just have the address of it, but if it's something simple, they might put it there. That's right. That's IDA trying to give it a descriptive name. So a hello is the pointer to hello. Very good. I'm glad you're asking. It's a good question. Anyway, so that's what function calls look like in IDA. All right, so you call, but before that you push things on the stack. And this leads to a lot of interesting security problems. And if you take our exploit development class, it's very interesting because this is a strange situation. This means when you call a subroutine like print, it assumes that you have put the arguments on the stack. If you forget to put the arguments on the stack or you make any mistakes, print will just go on the stack and interpret whatever it finds there as the arguments. So you can have weird problems, and there's a whole a fascinating vulnerability called the format string vulnerability, where you do not specify the format string and then the user can specify it. And you can, if you forget to put things on the stack, print will just print whatever it finds on the stack. It doesn't know that you actually prepared correctly. It just assumes by the time you come here, arguments should be waiting for me on the stack. I'll take whatever I find there and use it. Anyway, computers have sort of amnesia. They don't know what went before. They just execute the current instruction even if the context is wrong. So you can have global variables stored outside functions. This is an issue of scoping. You know, if you look at source code here, that's what these curly braces are. They define the scope. So this is the main routine scope. And if I define a variable inside here, it's only in this scope, and when I leave main, it'll be forgotten. But if I define it up here, it would apply to all the functions. So If I defined it up here outside that curly braces, it would be global in scope and be available to every function. But if I defined it within one function, it only exists while that function is running. And if that function stops, it will be discarded. So it's stored on the stack to be temporarily stored, because it only applies to a certain temporary period of the program's execution. And up here, it's stored in someplace else, like the data section, that is not ephemeral. So that's the game. Global variables stored outside all functions. These are stored on the stack. And every time you enter a function, it creates a temporary stack frame for the stack variables for that function. And when you leave, it releases that memory to be reused. So things on the stack only exist temporarily. So here I define a variable up here, a global in scope, and then another variable down here inside the main function. So G, here we have the two variables being, now we're going to print both of them, G and I. So first we're going to put the local variable on the stack, and then we're going to put the global variable on the stack. So you see EAX is just the variable itself, just sits on the stack, but the next one is a pointer to 41B100, and that's somewhere else in memory, like in the data section. So that's going to be the, all right, that's what happens. Then you print them both. So you can spot the different variables. The stack-based variables have pointers that are calculated from EBP typically, EBP plus something, from the base pointer, which is the base of your stack frame. It adds a variable which looks like, and that tells it where it is on the stack. So local variables are stored on the stack and just calculated from EBP or ESP, something like that. But other variables have these names, and IDA-Pro will give them a name like this, just an address built into the variable name, which means you go somewhere else on some other segment of the program where that is stored. All right, so here's arithmetic operations. You can have plus, minus, multiply, and divide, and you'll see them all. So here's add and subtract, and integer multiply, and here's a division, which is pretty messed up. Actually uses these floating point things to do floating point division, these XMM variables. Anyway, all those things exist in assembly. So global variables always referred to with another memory location. Yes, that's the idea, yes. Instead, and local variables are referred to like this, by some calculation from EBP or ESP, some local calculation that's only going to make sense inside this function, and when you leave this function, this won't mean anything anymore. Then you've got an if. So here I have if I greater than 0, print this, otherwise print that. So here I set a local variable I to be 3. The init I equals 3 is going to take 3 and move it into a location on the stack, EBP plus something. And then I'm going to do a compare that number to 0, and if it's less than or equal, I'll take the green arrow, and if that condition is false, I'll take the red arrow. So this compare followed by jump less than or equal is this if. And so then it does one thing or it does the other. That's what ifs look like. And here's a for loop. For I equals 0, I less than 100, print something. So you're going to have 4 components. This is a real compressed statement. You started at 0. You have a comparison, is less than 100, you have execution, and then you have increment or decrement. And so that loop will look like this. You initialize, this is apparently I, EBP plus variable 4, a local variable. You started at 0. Then you jump to 40106, 1016, here. Okay, you jump down here, and you did not do the increment this time. You compare this number to 100, which is 64 hexadecimal. If it is greater than or equal, then you're done, and you go off the bottom. If it's not greater than or equal, you go here. And now you move something and print something, and then you jump back up to here, where you add 1 to it. And I'm not sure what the rest of this nonsense is, but the point is this is the increment. So you increment, compare, and if it's not time to quit, you execute and increment and compare again. All that mess is what a loop looks like. All right. And then there's arrays. You can define an array that's just a whole series of numbers separated by commas. So that's a global array. Here's a local array, which is just set to a series of numbers. All right. And so you've got assembly code here. Increment, right, this is doing the loop. This loop for I equals 0 to 5. So increment compare to 5. And here you assign a value to element B, which is on the stack. EBP plus ECX plus 4 plus var 14. This is a calculated number from the stack. So this is a local variable having something assigned to it, and here's the global variable with an address like this, having something assigned to it. And because it's an array, it has an address for the base of the array, and then it has a index, ECX, times 4, because you see a lot of these because the bytes are referred to by their address, and the addresses go byte by byte, but in a 32-bit processor, they're used as words 32 bits at a time, so you want to skip 4 bytes at a time frequently. So you assign 4 bytes for each integer stored, and so I don't want to store one in ECX and one in ECX plus 1 and ECX plus 2. I need to do ECX, ECX plus 4, ECX plus 8, that sort of thing. So I take this index and multiply it by 4 to jump forward by 4s. That's the idea. Anyway, it makes sense, but it takes a little getting used to. As you can see, it takes like 4 times as many instructions to do anything in assembly than it would have in a language like C. Can you skip any amount of bytes? In principle, you can. You can write code that will skip any amount of bytes, but the most common thing you want to do is just store normal integers, and normal integers are typically 32 bits long in 32-bit code. So you can skip any amount, but typically when you're storing in C, when you're storing characters, you use 1 byte per character, and when you're storing normal integers, you use 4 bytes for characters. But there are like double precision integers and floating point integers, and those have different sizes. So this could in principle be all different sizes for different data structures. But the most common one is either 1 for characters or 4 for integers. Those are the ones you see most often. All right, so here's stuff we did to find the code. We've done this before in IDA Pro. You look at the strings and then go to cross-references to find the user code, because for some stupid reason, IDA always starts at some kind of internal system jumps. Function calls, you push things on the stack in reverse order, and then call. And we saw global and local variables. Global variables have an address and point to some other segment like the data segment, and don't change, remain even regardless of which function is running. But local variables are calculated on the current stack frame from the current base pointer, and when you're done executing that routine, that function, they're discarded. Arithmetic is the same thing. Put variables in registers, perform arithmetic, and then move the results back into variables. And branching, you compare something and then do a conditional jump, like jump 0, jump not 0, jump less than 0, that sort of thing. Is disassembling interpreted languages such as Python? Well, I've never done any disassembly on interpreted languages. In principle, each command in an interpreted language is individually reduced to machine language and executed, and I've never seen anybody inspect how that process goes. It's an interesting question. I've never seen that. In principle, it could have bugs and maybe be exploitable and stuff, but I've never seen it. The only thing I've ever seen is compiled code. Good question. There are bugs in interpreted languages too. So I'm not quite sure what tool you would use to analyze them, but the logic is fundamentally the same. All right. And so branching, then you have a conditional jump with 2 arrows, red for the false and green for the true. All right. Let's take a look at a Kahoot. And then I got several projects to show you. We are 126, project 6. Or chapter 6. turn on a light. I'll be back. All right. Guess I'm ready to go. Okay, what variables are on the stack? Yep, good. Local variables. All right, what's C construct? It's 3 boxes connected by arrows, like that thing there. That's an if, that's right. It makes a decision to follow the red arrow or the green arrow. All right, what's C construct? Construct is several pushes followed by a call, like that. That's a function. You push parameters on the stack and then you call the function and it looks on the stack to find the arguments. All right. All right, and what is that? Gword 41B1000. All right, that's a global variable, and that's why it has that address there, instead of being EBP plus 4 or something like that. All right, that looks like good enough initials to identify somebody. That isn't, though, unless you've used it before, which is possible. I know who that is. All right, good. So